Problem 28 in section 1.1. So we're given a function f over the interval, and we call this function Lipschitz continuous with the Lipschitz constant L if this inequality holds for any x and y from that interval. So if you can find an L that doesn't depend on x and y, such that it's just a constant here, such that for any x, y you plug in, this one also this always holds. Then this fundamental function is called Lipschitz functions or Lipschitz continuous function. Okay, so for the first question is to show that if function is Lipschitz continuous or satisfies Lipschitz condition here, it must be continuous. Second is that if f prime exists over the interval and the derivative of f is bounded by this L, the magnitude is bounded by L, then this function must be Lipschitz continuous with constant L. And the third is to give a function f that is continuous over a closed interval, but it's not Lipschitz continuous. Okay, so Lipschitz continuity is a very, very useful property. Luckily, in many cases, we do have Lipschitz continuous function, and the Lipschitz continuity function has very nice properties, and it's just a type of continuous function that is really, really, when we say continuous function is nice, but it still can behave very strangely. But the Lipschitz continuous functions are really, really nice. They're just almost differentiable. Actually, there's a result in real analysis saying that if a function is Lipschitz continuous, then it is differentiable almost everywhere. It just means that you don't really have a chance to land a point that is not differentiable. Okay, so but that's something about the Lipschitz continuity, and it's stronger than continuity. Okay, whereas we will show in the third part here, we can show that function is continuous but not Lipschitz continuous. Okay, so first show show part A. We want to show that if function satisfies the Lipschitz condition, then it has to be continuous. So to show that, we just name any point x, and then we know that for any epsilon, there exists a delta. We just say this delta to be epsilon over L, because this is still a positive number, right? Because epsilon and L are both positive. So for any x, for any y whose distance to x is less than this delta, we can show the following: the the difference between f of y and f of x is bounded by L times y minus x. This is due to the Lipschitz condition. And then this distance here is set to be smaller than delta, so that's why this is less than delta times L. But the delta is set to be epsilon over L, so that's why it's just L, epsilon over L, and this L canceled, we only have the epsilon left. So that means for any x, for any epsilon, we can find a delta such that this distance is less than delta epsilon as long as the y is close to x. The distance is less than delta. So this is the definition for continuity, right? That means the function is continuous at the point x. But we don't really specify what that x is. We just say arbitrary x. So because x is arbitrary, we know that the function f is actually continuous over the whole interval. It doesn't matter where this x is from over this interval. Okay, so that proves the part A. For part B, so now let's say we know the function has a derivative bounded by L over that interval. So now let's say for any 2 points, x and y, they're different. Then we know by the mean value theorem, there exists a point between them such that we call this point c x and y. That is between the point x and the y. And the f of y minus f of x is going to be equal to the derivative of f at this point, middle point, and times y minus x. And then we take an absolute value on both sides, then we just have this. But remember that the f prime is always bounded by L. That's why this is always bounded by L. And this part is the Lipschitz condition. So that means the function f is L Lipschitz continuous. So now the third part. So to construct the function, I just named one. There are many of others. You can get the idea from this example. There are many other functions that are continuous but not the Lipschitz continuous. So this function, square root of x, is continuous over 0, 1, but it's not Lipschitz continuous. Okay, so how do we show this? So the idea is this. So the idea is that if you look at this function, the square root of x looks like this, right? So you can see that the tangent line actually is vertical, right, at the point 0. So this is the x, this is the square root of x. So that means the derivative can be infinitely large when your point is really close to 0 from this side. Okay, when you're getting closer and closer to 0, the derivative is actually unbounded. And this is how we're going to use this fact. So to show that it's not Lipschitz continuous. Okay, to show that, let's name any number L, okay, any positive number. Then for this number, let's think about a point in the interval 0 to 1 over 4L squared. So this is a positive number. It just could be very small because L could be large. So for this point, we take the derivative. So this is any point between 0 and this 1 over 4L squared. We take the derivative of f and evaluate that point. So when we take the derivative, we know that the derivative of the square root of x is this, and because x is smaller than this, so x is smaller than that. That's why when we put down the denominator is going to be greater than this, right? So it's going to be greater than this. This way. But when you do this from cancellation, then simplify it, it's just L. So that means for any point x that is close to 0, their derivative is going to be greater than L. Okay, so that means their slope is actually, the slope of the tangent line is actually very large. It's even larger than L. Now, for any point x and y, also in this interval, y could be less than x, or the other way around. As long as these 2 points are both smaller than this, then you can see that by the mean value theorem, there exists a point cx of y that depends on both x and y, such that the fy minus fx is going to be the derivative of f at this point times x minus 1. And then I'm just taking the absolute value on both sides, the equality still holds. But from here, you know that because this point is between these two things, so that means it's also less than this 1 over L squared, 1 over 4L squared. That means the derivative at this point must be greater than L, as we show here, right? As long as the points from this interval, the derivative is going to be greater than L. That's why this is going to be greater than L. So that means f is not does not satisfy the Lipschitz condition with L as the constant, as the number, Lipschitz constant. But we didn't really specify what this L is. It could be any number, arbitrarily large as you want. So that's why it cannot be Lipschitz continuous, right? Because this L is just arbitrary.